So this time we're going to discuss on Lorentz velocity transformation. Okay. So let us start on these two. We're looking at these two frames. We have two frames here, the S frame and the S prime frame. This was discussed already in the previous lecture about Lorentz transformation on time event and length. So there are two reference frames here. We have S frame, the rest frame, and then the moving frame at constant speed u is S prime frame. And there is event, that's point P, that's the event according to S prime, whose speed is V, that's according to according to the S frame. Now, the moving frame will move at a certain distance, which is the speed of the moving frame times the time. So that's the distance between the origins of the three axes. Okay. Now, imagine there's car here, car, okay, and then it's moving at the speed u. Okay, that's the frame, moving frame, and here you are looking at the car. You are at rest, and then you can see that this car is moving along x-axis at the speed of u, and the headlight emits a light, and we know the speed of light is c, right? So as you can see, the observed speed here, according to Galilean transformation, will be v, the observed speed, will be equal to the speed of the moving frame. The moving frame here is the car, which has a speed of u plus the speed of light c. Okay, so this is according to Galilean transformation equation, but it will contradict the second postulate, Einstein's second postulate, that states that the speed of light is the same in all reference frame. So the Galilean transformation is only good if the speed u approaches to zero or very small compared to the speed of light. So here, for second postulate, the speed of light is the same in all reference frame. Either the frame is moving or at rest, or the light is moving towards you or moving away from you. The speed of light is the same in all observers. Okay. So here, you can see when you add u to the speed c, so it means you can observe speed that is greater than the speed of light. Again, it contradicts the second postulate. So we cannot apply the Galilean transformation here because we know the speed of here, the speed is greater than speed of light. So rather, we will use the relativistic addition of velocity. Okay, so both distance traveled and time of travel are different in two frames of reference, and they must differ in a way that makes the speed of light in all inertial frames should be same. So we can obtain the correct rules for transforming velocities from one frame to another by using this transformation, what we call Lorentz velocity transformation. Right? The Lorentz velocity transformation is also known as the relativistic velocity addition. Okay? So V here is the speed. V is the speed of the event observed in the S frame. And then we know that the length or the distance from y prime, which is x prime, okay, that's the distance of point P from y prime, is given by this equation. Okay, it is expressed by this equation. This is the distance from y prime according to S prime. And the time of event in S prime frame will be this one, t minus the speed of the moving frame times x over c squared times the gamma. Okay. And then we know the velocity is the derivative of the space with respect to time. So this is v equals dx over dt, and this is the velocity in s frame. So that is the velocity observed in rest frame. And v prime is the observed velocity by relative to s prime frame. So that will be the derivative of x prime with respect to time, or v prime equals dx prime over dt prime, right? Velocity. So by using this equation, v prime equals dx prime over dt prime, so we will replace x prime by this x minus the speed of moving frame times t times gamma, and then replace t prime by t minus ux over c squared times gamma, right? So we can cancel gamma here, and then multiply each term by 1 over dt, or multiply the whole thing by 1 over dt per 1 over dt, and this is just equal to 1. So 1 over dt times dx, then we have dx over dt, minus u dt times 1 over dt. It will have a dt over dt, and that is equal to 1. So that's why we have u here. And then dt times 1 over dt, that's dt over dt, and minus du x over c squared times 1 over dt. Then we have u dx over dt per c squared. Okay, so we can cancel dt here, so what is left is u, and dx over dt again is the velocity in s frame. So we have uv over c squared at this part. So this part, dt over dt, is equal to 1. So v prime, the velocity observed in the moving frame, will be the v, that's the speed observed in the s frame, minus u, the speed of the moving frame, or s prime frame, over 1 minus u v over c squared. Right? So this is the speed observed in s prime frame. The principle of relativity tells us that there is no fundamental distinction between two frames, S and S prime frame, but U is in opposite direction. With V, change to V prime and vice versa, and assign U reverse. So we find, we're looking at this equation, V prime equals V minus U over 1 minus UV over C squared. Then the speed observed by the rest frame, the S frame, will be equal to V prime plus U over 1 plus UV prime over C squared. Okay, so we just change the sign. So in this equation, we have negative U, right, both numerator and denominator. So this equation will have positive U for numerator and positive U for denominator. Okay, there's no distinction between two frames. Like the observer in S frame will see that the moving frame is moving along the positive x-axis, while the observer in S prime frame will see that the S frame will moving in negative along negative x-axis. Okay, so the only difference there is the direction, okay, not the magnitude of velocity. But take note, all these equations only define the motion of moving frame whose velocity is u, and the velocity of the event in S prime frame, which is v, will be that is moving in the positive x direction or along x direction. Okay, so that's for the Lorentz velocity transformation.